In today's lesson, 11.6, we'll be taking a look at areas of circles, sectors, and segments, looking at a few formulas along with a few examples on how to calculate these. Going back to some things that hopefully you learned in previous years, the area of a circle is equal to pi r squared. A quick definition that we've seen in previous sections is a sector. And a sector is a bounded region bounded by two radii in an arc of the circle. So if we have a circle with two radii, as you hopefully remember, the sector would be the area in between the two. We can calculate the area of a sector by taking the angle measurement, dividing it by 360, and then timesing it by pi r squared. And we've talked about this in previous lessons, because basically you're taking a portion of the 360 circle, that's this part right here, and then from that, taking it from the entire area. Something you may or may not have heard of in the past is a segment, which is a region bounded by a chord of the circle and its corresponding arc. So if I have a chord drawn here, this would be the segment area of the circle. Now, one thing we'll want to know is how do you calculate the area? Well, let's say this is the center, and I draw a line to each endpoints of the chord. And you'll notice that basically now we have a sector. And within that sector, you have a triangle. So what you're going to do is basically you're going to calculate the area of the sector and the area of that triangle and take the difference of the two. So the area of the segment is equal to the area of the sector minus the area of the triangle. Alright, first we have our first example. And what we're going to do is we are going to calculate the area of the segment. And what we'll know is we'll know that the radius is 6, and we will know that the arc measurement right here is 120 degrees. So there's two things we're going to want to calculate. First thing we want to do is we want to calculate the area of the sector. And again, that comes from the angle over 360, so it's that portion of a full circle, times the full area, which is pi r squared. So it's going to be pi times 6 squared. So that's 1/3 times pi times 36, which gives us 12 pi. And again, that's the full sector. What we're really looking for is we're looking for the area of the segment, which is this part in here. So now what we want to do is we want to then basically find the area of that triangle. So we're going to need to calculate the area of the triangle. And you know that the area of a triangle can be found by half times base times height. So we'll need to be able to figure that out. Base times height. To calculate the base and the height, we'll have to do a couple things. We'll draw a perpendicular line to the chord, and since this is 120, that means this angle in here is 120, and since this angle, we know from previous theorems, is a bisector, that means that this angle is 60, If that's 90, this has to be 30. So we have a 30, 60, 90 triangle. This would be 2x. Therefore, this would be 3. And half of this chord right here, that would be 3 square root of 3. So our base would be double 3 square root of 3. So it would be 6 square root of 3. And our height would be 3. So our entire area of our triangle would be 9 square root of 3. And again, to calculate the area of the segment, we do area of the sector minus area of the triangle. So it's going to be 12 pi minus 9 square root of 3. Our second example, we have the area of a sector with a circle with radius 6 is 15 pi. We want to find the measure of the arc cut off by the sector. So we go ahead and we draw our circle. We know that the radius is 6 again, like the previous example. This time, though, we want to know the measure of the arc cut off by the sector. So here's the sector in here, and we want to figure out what that angle is, or the angle measurement of the arc. Well, we know from our formulas that the area of a sector can also be calculated by the angle measurement over 360 times pi r squared. And we're given that the area is 15 pi, so we'll substitute that in. We know the radius is 6, and we'll start calculating. Cancel out the pi's, reduce the 36 over 360, and x, the measure of the arc, is 150 degrees. And finally, our last example. A circle inscribed in a square with side 16, which is inscribed in another circle. And what we're trying to do is find the area of the outer ring formed by the two circles. So what we know is that the square has a length of 16. So from here to here, and those circles should be touching the edges because it's inscribed. So that means that the diameter is 16, therefore the radius is 8. So if we call the inner circle, circle 1, so circle 1, the area would be pi times 8 squared, which equals 64 pi. Since the square is inscribed in here, and with a square it's 40, a line can be drawn to create 45, 45. So if this is 16, the length right here will be 16 square root of 2. Again, thinking back to the ratios of our 45, 45s. And so therefore the radius of the larger circle is 8 square root of 2. So pi times 8 square root of 2. And And that gives us 128 pi. And again, we're looking for the ring being this. So it's the difference between the two. So 128 pi minus 64 pi gives us 64 pi for our area.